Hello, welcome back to EEforEveryone in part 10 of the Plant Light Project series. Today we're going to measure the performance of the voltage regulators on the power board. We will take a look at the ripple performance of the regulators under load and the ripple performance while they're unloaded. Unfortunately, I didn't consider efficiency tests when designing this board, so it isn't really convenient to probe the voltage and currents of each regulator's input and output independently. Therefore, the best way for us to get through all of these measurements pretty quickly is to measure the power coming in from the wall and then the voltage and current coming out of each converter with a known load. What this means is that the efficiency of the AC to DC converter will be a factor in all of our measurements, but as long as it's accounted for, it shouldn't have a huge impact on the accuracy of our results. If this is truly the case, we should expect that the 6 volt, 12 volt, and 5 volt linear regulator should all appear to have worse efficiency than the 24 volt supply on its own. To make sure that that's actually the case, we're going to measure that and verify when we're done. The efficiency of all of these switch mode power supplies varies with load level. At very light loads, the switch mode power supply would typically have worse efficiency at near 50 to 80% low. The efficiency also drops off a bit as the load reaches 100%. This will introduce some noise into the measurements when compensating for the AC to DC converter and our other measurements, since the load level won't be exactly the same. But we don't really need a ton of accuracy in these efficiency measurements, since we're not looking to characterize it, we're looking to verify that the design is performing as expected. In reality, the switch mode power supplies will be efficient enough that their power draw will likely be considered insignificant when compared with other appliances around the home or the LEDs themselves. Without a lab power supply, we also are unable to conveniently measure line regulation. Line regulation is a measure of how much the output voltage of a power supply varies with a change in input voltage. Since we're loading the regulators with power resistors and not an electronic load, we won't have many data points for load regulation either. If the data suggests that a regulator has poor load regulation performance, we'll dig into this further. Since we're using these regulators in a configuration very close to what the manufacturer recommends, I imagine that the load regulation will be as specified in the datasheet for the controller IC, and we won't need to spend too much time investigating the line or load regulation. Even so, we can plan to dig into line and load regulation in a future video after a lab power supply is in the budget. The main purpose of these measurements is to see that each switch mode power supply is operating with an efficiency near 91%, and that the combined 24 volt to 6 volt buck/linear regulator combination has an efficiency near 77%. This is what we predicted in part 2 of the Plant Light Project series, with the converter loaded with 100 milliamps. This, of course, will be after we compensate for the losses in the 24 volt AC to 24 volt DC switch mode power supply. I'm amped for these measurements, so let's get to it. So just to walk through the tools real quick, we've got the kilowatt meter measuring watts from the wall. We've got the unity multimeter measuring current, and then a less reputable multimeter measuring the voltage. It's just, well, this was actually a kit that my school had us do. It was like the first year teaching you how to solder. It's all through hole. It's probably not great, but for a DC voltage measurement, it's been good. That's why I'm using the better multimeter for current, since it's a more involved measurement and there's more that can go wrong. So, yep, this one's actually rated with a tolerance, and accuracy, so I trust that one a lot more than this one that I built by hand when it comes to current. So, digging into this, I need another alligator clip. Got a pile of alligator clips. The reason why we need these alligator clips is because when I was prepping for this episode, I didn't add enough impedance for the 24 volt measurement, which was a shame. These are all 10 ohm power resistors. There aren't anything special, 10% tolerance. We're not using them for like a current shunt or anything that requires a lot of accuracy, so I didn't see a reason to break the bank here. What we're really trying to do is load down the regulators to a certain current level, and I can always swap out a resistor if I need to. We'll hook this positive side up to 24 volt, can see we have 300 milliamps of current flowing. We have 24 volts on the output. 24 volts. Current output, 0.3093. Wall power says 8.8 watts. Look at that. Let's unload the power supply. 24.1 volts. Wall power of 0.5. 0.5 watts. Me up. Yeah, sure enough, 0.5. All right. That's pretty good efficiency. Righto. Moving on to the 12-volt regulator. Unloaded, since the DC negative side of the current probe is not connected. The input voltage is the unloaded 24 volts. The output voltage is 11.9. We'll get to ripple in a separate measurement. Wall power is again 0.5. V out. Alright, now we need to load it. 200 milliamps. 11.86 volts. 0.2074. Again, we'll get to the ripple measurement in a moment. Wall power 3.6. Perfect. The 6-volt regulator. The input voltage is again the 24 volts. Output voltage 5.99. Ripple, we'll get to that. Wall power 0.5. V out. When we load it, .86. I out 0.172.4. It's my multimeter kindly reminding me that it wants to turn off. Alright, there we go. Ripple voltage, we'll get to that. Wall power says 1.6. Now, I think the main reason why that measurement's low is because we're pulling less power through the kilowatt. So its accuracy, which isn't very good compared to the other measurement equipment, the accuracy isn't very good on the kilowatt meter. Ideally, I would load this down more. But since our final current measurement is going to be 100 milliamps on the linear regulator, it really doesn't make too much sense because we're going to get that same inaccuracy. Likely the efficiency should have measured more like 79-80% since they are literally the same design. But we can look into that. We can take a look at the data sheet for the switch mode power supply controller and see what it rates the efficiency for with this input and output voltage. 5-volt regulator side. Oh, unloaded first. We have 5.99 volt. Output voltage is 4.97 and 0.5 on the kilowatt meter once again. Load it down. Should be around 100 milliamps. Yep. So the output voltage has dropped to 4.6. Output current is 0.098. Wall power reads 1.3. Here we've got some data. Looks like I need to switch around our measurement setup, get the waveforms window up here, and then we can measure the ripple. We have the oscilloscope. hook up the electrodes. Now I'm hoping that the ground shift won't be an issue this time. And if it is, I've got a way to fix it this time. So since the AC to DC converter is a isolated supply, it has to be for regulatory reasons, we can actually tie the negative of the scope probe to ground with respect to the oscilloscope. Since this is an isolated supply, it should be able to handle the leakage current without inducing much ground shift, where before, I suppose technically we could have done the same thing. Yeah, we could have done the same thing last time. Sorry about that. Many people will immediately realize that as far as measurement setups go, this one is pretty not ideal. It is not ideal. There's a lot of opportunity for noise to couple in to the signals I'm trying to measure. That is certainly the case. But since the oscilloscope isn't that good to start with, I don't mind. It doesn't bother me. Oh. So it looks like there is indeed some noise coupling in here. Before I go and do something dumb, like if this wasn't an isolated supply, technically I just got it off Amazon, so it could be anything, sold from anyone. We're going to add a resistor in series, and if the ground shift goes away through a 1K ohm resistor, we know there isn't much current at play. I am 99% sure this is an isolated power supply. Yes, so notice without tying the ground plane of this board to ground, there's 120 volt AC coupling in. Tying that to ground through the 1K ohm resistor to protect the scope is able to attenuate that noise to basically nothing. Oh, works better when you plug it in. Hey, look at that. You can see 24 volts with very small amounts of noise. Negligible amounts of noise. Take this over to our 12 volt supply. See, there's also a very small amount of noise. That's wonderful. But what if we load this 12 volt supply? Wonderful. Still very, very small amounts of ripple. There's even though there's 250 milliamps flowing, this regulator is able to keep up just fine. And the 6 volt regulator, we should see the same thing. Absolutely. 6 volt output, very little noise under load. Take this over to the 5 volt rail. What do we see? Also, very, very clean. What this tells me is that either the bandwidth of this scope isn't high enough to measure the noise that we are seeing, or power supplies are very noise-free. Linear regulator output looks very stable. But it looks like as we zoom in, there is a high frequency ripple. Let's add an FFT. Look at that, a pronounced peak around 500 megahertz. I wonder what that could be. Let's try the 5 volt rail. Let's see what happens at that 500 megahertz frequency. It's still there, but the ripple appears to be attenuated. So this is showing a magnitude of around 45 dB volts as opposed to 40. So it has attenuated the ripple by about 5 dB, which is less than half. If you're familiar with these measurements, the conclusion is obvious. There's less voltage ripple on the 5 volt rail than there is on the 6 volt rail. But there's very, very little ripple on both. I think we should put our power board in there, power it on, removing the load here, of course, and take a look at what happens to the voltage rail. So it looks like we're very realistic with our current approximation because the voltage has dropped to 4.6 volts. We're at 100 milliamps, that would have dropped to 4.5, so this is consuming somewhere around that amount of current. And we can see that with this load level, there is no appreciable voltage ripple on the 5 volt supply at all. That is perfect. Check the 6-volt rail, and there are some pronounced peaks at 500 kilohertz, 0.5 megahertz. What does this tell us? Same thing as before. Under normal operation, without a resistive load, there is no appreciable ripple, at least that I can measure with the analog discovery, on the 5-volt output, but there is some ripple on the 6-volt regulator. But what does this mean for our measurements here? Well, the magnitude is so small in all cases that if I were to put a number there, I wouldn't be sure whether I was seeing ripple because my measurement isn't accurate enough, or if I'm seeing ripple because it's actually there. It's an interesting thought, and it's something that is really the reason why I try to buy tools that I can trust, because if I can't trust the tool I'm using to make the measurement, I can't trust the measurement. In this case, these are tools that I've used a lot, and I'm confident in saying that I wouldn't be able to tell the difference between noise in this ripple measurement and this signal. So, looks like if we want to dive in further, I'm going to need to buy a better scope. Let's hope that's true. I'd love to get a new scope. So, conclusion time then. What does this efficiency measurement tell me? This efficiency measurement tells me that the AC to DC converter is about 90% efficient. About 10% of the power is lost in this switch mode power supply. So that means for every other efficiency measurement we made, we need to add that 10% back in, because that 10% was probably consumed by the AC to DC converter. So that means our 6-volt buck was measured at around 80% efficient. The 5-volt regulator was measured at around 65% efficient, and that the 12-volt regulator was measured at around 90% efficient. So that is very, very close to the 91% and 72, I think it was 72%. And since the input power measurement didn't have a high degree of accuracy, I'd say that's within the margin of error of this measurement setup. We can take a closer look at efficiency of this system once we have that benchtop lab power supply. And I think that we should. I hope that you enjoyed these workshop videos where we have some fun, take some measurements, and ensure that our design is performing as expected. I've really come to enjoy this time in the shop with you, just sitting at the workbench, and I plan to do more videos like this in the future. If you think that efficiency is cool and this video is great, let me know by hitting the like button on this video, subscribing to the channel, and leaving a comment letting us know what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. Bye!